Hello. In this video, I will explain to you about naming of compounds in general, specifically naming of alkanes, and more specifically acyclic alkanes, meaning those without rings. Furthermore, I'm going to break it down into two systems of naming. The common system we'll cover in this video, and then in the next one, we'll talk about the IUPAC system. Common system is simpler, but not as useful, and it was developed historically to give names to compounds as they were discovered. In other words, historically developed over time. Turns out not to be that great of a system, but there are still some names that are very commonly used, so we need to learn the common system. Again, I'm going to suggest that you read section 2.3 before you view the video, and it will explain more than just what's in this video, but it will give you context for what we're going to be talking about here today. Start with the simplest organic compound, which is methane, just CH4. 1 carbon, 4 hydrogens, tetrahedral, as you would expect, and it's called methane. That was a name that was historically developed for it. As it turns out, that's the only name for this compound. Everybody calls it methane, whether common system, IUPAC system, or anything else. The next simplest organic compound is ethane. That's 2 carbons, 3 hydrogens on each, 1, 2, 3, 1, 2, 3, so it's CH3, CH3, molecular formula C2H6, ethane. Again, that's a historical name for it. One thing you'll notice about ethane, which is obvious in this model, not necessarily in structures you might draw, is that since each carbon is tetrahedral and there's a single bond in between, you can rotate around that single bond, which means there are several different conformations of ethane, depending upon how the two carbons are oriented with respect to each other. But we'll talk about that at a later time. As it turns out, in an actual sample of ethane, all of those conformations are present, and you can't really separate out one from the other, so the whole thing is just called ethane. The next most complicated is propane, and that's 3 carbons, so it's CCC. This carbon has 3 hydrogens, this carbon has 3 hydrogens, this one has 2, so it's CH3, CH2, CH3. Molecular formula C3H8. Now you'll notice one thing that I've done on this slide that I didn't do on the previous two is draw the line angle formula. I can't really do that for ethane or methane. There's only 2 carbons or 1 carbon, so it doesn't really make sense to do that. But remember, this means CH3, CH2, CH3. And you'll notice that, like ethane, you can rotate around single bonds, but since there are 2 carbon-carbon single bonds, you can rotate all sorts of different ways. Those conformations are all present in a real sample of propane, not able to be separated out from each other, and so the whole sample is just called propane. Now, when we get to butane, which is 4 carbons, we put this little N in front, and we'll talk about why that's there in a couple minutes. But notice that this is CH3, CH2, CH2, CH3. I happen to have a model of that. Notice 4 carbons in a row, 1, 2, 3, 4, CH3, CH2, CH2, CH3. Notice you can rotate around all of these carbon-carbon bonds, so there's a number of possible conformations there. But again, rotation occurs naturally in a real sample, and you can't stop it, and you can't separate the different conformations out from each other, so the whole thing is just called butane, or in the common system called N-butane. I've drawn the line angle formula for you, CH3, CH2, CH2, CH3. Common name, N-butane. And following that same pattern, we have 5 carbons in a row, CH3, CH2, 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 CH3. That's called pentane. Now you notice that this is the first time where the prefix in the name refers to the number pent, means 5 like pentagon. We still have that little N in front, and we'll explain why, as I said, in a minute. Hexane, and hexane has 6 carbons in a row, CH3, CH2, 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 CH3. So in hexane meaning 6, hept meaning 7, oct meaning 8. One thing you may notice is how the formulas change. For 5 carbons, it's 12 hydrogens. For 6 carbons, it's 14. For 7 carbons, it's 16, and so on. There's obviously a pattern there. And 9 carbons in a row would be called N-nonane. 10, because non means 9. Dec means 10, like in decade. So decane is C10H22. N-decane means all in a straight line. And then after that, we just add a prefix in front of decade. So undecade means 11. Dodecade means 12. Tridecade means 13, tetradecade means 14, and so on, pentadecade. When you get to 20, C20H42, if all 20 carbons are in a row, no branches or rings, then we call it icosane, and that's what the N means, no branches or rings. Now, let's back up to butane. As we saw a minute ago, butane is 4 carbons in a row with a total of 10 hydrogens. But there's also another compound with 4 carbons and 10 hydrogens. Notice that's those 10 hydrogens, so they have the same formula, C4H10, but they're obviously not the same molecule. Or perhaps you're not convinced that they're not the same molecule, but look at the groupings. CH3 attached to a CH2, and then another CH2. Notice in this molecule there are no CH2s. There are 3 CH3 groups. Here there are only 2 CH3 groups. Here there's a CH. Here there is no C with a single H on it. And here is a model of that second molecule. This one's C4H10, but 1 carbon in the middle and 3 CH3 groups attached to it. The carbon in the middle just has 1 hydrogen. These are clearly different compounds, different structures at least. The fact is they are different compounds. They can be separated into different bottles, and they have different properties. So they'll have different boiling points, different melting points. They probably smell slightly different, a different amount of energy when you burn them, and so on. So these are what we call isomers. Isomers are 2 or more. In many cases it's more than 2. In this case only 2 compounds with the same formula but with different structures and therefore different properties. The problem is, what do we call it? So that first one we called N-butane, and now we know why we needed the N, because there's another one. This was called isobutane, where the iso prefix was added because it was an isomer. So isobutane is an isomer of N-butane. And it has turned out that the iso is always going to mean that you have a CH3 and then a CH and then a CH3 in the same molecule, and then the rest of the carbons, however many there are, will stretch out in a straight line from the center of the CH3CH3 group. So this is isobutane. So there's N-butane and isobutane, different compounds. So you can see that the system is going to be here as we get more and more isomers. We're just going to add more and more prefixes in front. So, but let's continue talking about isos for just a minute. Isopentane has that same CH3CH3 with the rest of the carbons strung out from there. Isohexane, CH3CH3 with the rest of the carbons strung out from there. Isoheptane, CH3CH3 with the rest of the carbons strung out from there, and so on. Now, one thing to notice in all of these molecules, whether it's isobutane, total of 4 carbons, so but means 4. It's 3 in a row with 1 coming off it, but it's a total of 4. Pentane, isopentane, has a total of 5 carbons, so C5H12, exact same formula as what we saw a minute ago for N-pentane, C5H12, but they're arranged with 4 carbons in a row and then 1 attached to it. So it's CH3CH3, so that's isopentane. Isohexane, again, total of 6 carbons, 5 in a row with 1 attached to it. Isoheptane, 6 in a row with 1 attached to it for a total of 7. Isooctane, 7 in a row with 1 attached to it for a total of 8 carbons, and thus octane. So again, this number in here refers to the total number of carbons. Now, let's go back to 5 carbons, and we saw that so far we've seen that there are 2 isomers of pentane, N-pentane, which is 5 in a row like this, isopentane, which is 4 in a row with 1 attached on the second carbon. It's called isopentane, but it turns out there's actually 3 isomers, all with the formula C5H12, and the third one has 3 carbons in a row with another CH3 attached to the middle carbon and another CH3 attached to the middle carbon. In other words, a carbon in the middle with no hydrogen, and a CH3, another CH3, another CH3, another CH3. I have a model of that as well. Notice a carbon in the middle and 4 CH3s attached to it for a total of 5 carbons and naturally a total of 12 hydrogens. And so that's what's called neopentane. And it has a separate existence. It's got different properties, different boiling point, different melting point, and so on, from isopentane and different from N-pentane. What does the neo stand for? The neo stands for new. So this was the newest isomer discovered. There's really nothing any newer about neopentane than any other pentane, but since it was the most recently discovered, they called it neopentane. I think you can begin to realize that we're going to begin to run into trouble when we get bigger and bigger and bigger molecules. They're going to have more and more isomers. It's going to be difficult to keep coming up with new prefixes. So this is isopentane, 4 in a row with 1 coming off the third carbon, or is that the second carbon? Well, I guess it depends on which way you count. That's an important idea. So common name, isopentane. So let's look at this structure, which I said a minute ago was isopentane because it's CH3, CH, CH3 with the rest of the carbons coming out in a line like that. And then this one, which is CH3, CH, CH3 with the rest of the carbons coming out like that. The question is, are these two representations of the same molecule? Answer, clearly yes. If you just take the one and turn it around backwards, then you get the other one. Do they have the same name? They have to if they're the same compound. So in fact, they are both called isopentane. And that's there just to illustrate the fact that just because we draw it backwards doesn't make it a different compound. Okay, and then finally, here's neopentane, common name you need to know. So let's add a couple more in the same series. Neopentane has CH3, CH, CH3 on a carbon with the rest of the molecule coming out this way. Neohexane, as you might guess, also has CH3, CH3, CH3 on a carbon with the rest of the carbons coming out that way for a total of 6 carbons. And neoheptane, as you might guess, has CH3, CH3, CH3 on a carbon with the rest of the carbons coming out in a row like that. So that's neoheptane. Again, a total of 7 carbons. And you can go ahead and draw what would the structure of neooctane look like, what would the structure of neononane look like, what would the structure of neodecane look like. Just remember that this number prefix in here refers to the total number of carbons. So this is a total of 5, this is a total of 6, this is a total of 7, and so on. Okay, now let's look at these two molecules. Are these two representations of the same molecule? This is 5 in a row with a CH3 group on the second carbon. This is 5 in a row with a CH3 on the third carbon. Are these the same as each other? In other words, if you just turn one backwards or upside down, would it be the same as this? And the answer is no. This is quite clearly a different structure than this one. One way of knowing that is by giving them names. But if you don't know they're not the same as each other, then how do you know that they have different names? Well, let's look carefully. Notice that this, a single hydrogen on a carbon, in other words, a single CH group with a CH3 on one side and a CH2 on the other. This has a single CH with a CH2 group on one side and a CH2 on the other. So this CH is different in this compound than it is in this compound. Therefore, they are different compounds. So, do they have the same name? And the answer is absolutely not. They cannot have the same name since they are different compounds. And that's one of the rules of naming is you can't have two compounds with the same name. So the first one is called isohexane. And what are we going to call the next one? Well, unfortunately, at this point, they kind of threw up their hands and they said, you can't keep coming up with new prefixes. It's going to become impossible. So this one does not have a common name. And so that illustrates why we need a system like the IUPAC system for alkanes, as well as we will see IUPAC system for every other kind of compound we come across: alcohols, alkyl halides, ketones, carboxylic acids, amines, and so on. And we will learn those as we go along, but they all depend upon knowing the naming system for alkanes. So that's why in the next video, you will learn about the IUPAC system for naming alkanes. Okay, now let's take one more little side trip here. We have to also learn the names of some alkyl groups. Now, what is an alkyl group? Well, for example, this is an ethyl group. It's a CH3. Notice that it doesn't have an octet. It's not a molecule. It doesn't exist by itself. It is only found as a group that might be attached to another molecule. Like, for example, we saw in these molecules, here is a CH3 group attached to something else. This is called a methyl group, and we will come across that a lot. So methyl is a really important group. It doesn't exist by itself, but it only exists attached to other things. So for example, here is methyl group attached to a bromine. It's called methyl bromide. You don't need to know the name of that yet, but I think you might see that it kind of makes sense. Here is a methyl group attached to an OH. The common name of that is methyl alcohol, and we will learn that name later on as well. Here's just another example. Here's a CH3 group attached to a 6-carbon ring. It's called methyl cyclohexane. So I'm giving you these not so that you need to know those names, but just so that you see that a CH3 group is called a methyl group. By the way, sometimes alkyl groups, methyl group is an example of an alkyl group, are called radicals. They don't have existence by themselves, at least not normally, but they are groups that you will find attached to another group in a real molecule. Similarly, a CH3CH2 attached to something else would look like this. CH3, CH2, and then a space here for it to be attached to something else. This is an ethyl group, And you find ethyl very commonly attached to other things. And again, I gave you some examples: ethyl bromide, ethyl alcohol, ethyl cyclohexane, and so on. One thing to notice is that an ethyl group has a methyl group in it, but it's not named as a methyl something, it's named as an ethyl group because it's just a CH3CH2. Now, here are some common names of propyl groups. There's only one methyl. I showed you what that looked like. There's only one ethyl. I showed you what that looked like. Again, here is the methyl group. It's a carbon with 3 hydrogens, but it has to be attached to something else. And here is the ethyl group. 2 carbons, 5 hydrogens, but it has to be attached to something else because you can't just have nothing attached to that carbon at that 4th position. But by the time you get to propyl, there are 2 different propyl groups. So in a sense, they are isomers of each other. You can have 3 in a row with the attachment at the end. We call that N-propyl, which kind of makes sense because it's 3 in a row attached at the end. But then we also have isopropyl, in other words, 3 in a row attached at the middle. That's a different alkyl group, even though they're both 3 carbons and 7 hydrogens. They are different from each other, so they have to have different names. This one's called N-propyl, this one's called isopropyl. I've drawn isopropyl in 2 different ways here, but it's still CH3, CH3 with a point of attachment in the middle. This is CH3, CH3 with a point of attachment in the middle. It can be drawn either of these 2 ways or many other ways, as long as you have CH3, CH3 with a point of attachment. This is called isopropyl, and you'll notice the familiar iso group, which is the CH3, CH3. So 2 propyl groups, and you have to know both of those names very commonly. There are 4 kinds of butyl groups. There's N-butyl, which you can imagine is 4 in a row with a point of attachment at the end. There's isobutyl, which is CH3, CH3 with another CH2 group attached to it to make it butyl, but it's iso because it's a CH3, CH3, and then the point of attachment is over here. But then we also have a new one called sec-butyl. We've never seen that sec prefix before. Basically, it just means that the point of attachment is on the 2nd carbon of 1, 2, 3, 4, so it's sec-butyl. And there's also a thing called tert, which, by the way, is short for tertiary. We'll learn about that later on, or sometimes called T to simplify the tert. That would T. T-butyl is 3 in a row with a methyl group coming off the 2nd carbon, just like this is 3 in a row with a methyl group coming off the 2nd carbon, but the point of attachment is in the middle here instead of being on the end as it is here. So this is a T-butyl group, this is an isobutyl group, this is an N-butyl group, this is a sec-butyl group. Now I will warn you, these 4 groups are very commonly used. We will run across them again and again and again in organic chemistry, and so you'll need to not only be able to recognize which one is which in terms of if you see the structure giving it a name, but also if you see the name being able to draw the structure. And I will tell you that many people don't have trouble recognizing and drawing N-butyl. Most people don't have trouble recognizing and drawing T-butyl. Oh, by the way, that should be a CH3 there. That's a mistake. That should be CH3. This should be a CH2 because, of course, it's attached there. But most people have a little trouble distinguishing between isobutyl and sec-butyl. Not sure why, because they're really nothing like each other. This is 3 in a row with a carbon attached. This is 4 in a row. Here the attachment is at the end. Here the attachment is on the 2nd carbon. And yet people sometimes have trouble distinguishing these 2. So you want to draw different examples of these and name them. And of course there are several different ways of drawing this, and there are several different ways of drawing this as well. Now, here are some pentyl groups. Notice that there are 6 of them. Again, we run into the problem of running out of prefixes. You hopefully will recognize this as N-pentyl because it's 5 in a row with point of attachment at the end. This is isopentyl because it's 4 in a row, but there's a CH3, CH3 with the rest of the molecule coming out here, point of attachment at the end, so that's isopentyl. There's neopentyl, which is CH3, which is CH3. There should be C, no hydrogen there, sorry about that, that's a mistake, and then CH2. So neopentyl is 5 carbons, 3 carbons in a row, methyl group coming off 2nd carbon, another methyl group coming off 2nd carbon, and then CH2. That's kind of like neopentyl. This one, you might say, well, maybe that's sec-pentyl, and probably most people would recognize it if you called it sec-pentyl. But then what are we going to call this one? It's not T-pentyl, because this is T-pentyl. T-pentyl is CH3, CH3, with a point of attachment in the middle, and then the rest of the carbons coming out this way. This one doesn't have a particular name. This one doesn't have a particular name. So the problem is we just run out of prefixes. So we're going to have to have an IUPAC system, not only for alkanes, because we run out of prefixes for alkanes, but also for alkyl groups, because clearly we run out of prefixes for alkyl groups. So we will talk about the IUPAC system in the next video. Thank you for your attention.